Hello students, welcome back. The final topic left for section 3 is the proof of Bezout's theorem. This one right here. Given pair of integers a and b, there exists a non-negative common divisor d of a and b that is non-negative. In other words, d should be greater than or equal to 0 and it's an integer, so 0, 1, 2, 3, 4 and so on. In other words, d is a whole number, as I just highlighted in green. And the common divisor of a and b, that means d must divide a and also d must divide b, as I just highlighted in blue. Alright, green and blue, first condition and second condition of this Bezout's theorem. Where were we? Yeah, given pair of integers a and b, there is a non-negative common divisor d of a and b of the form, of this form, the linear combination form, d equals to ax plus by, where x and y are integers. So, this theorem consists of three parts: green, blue, and red. Non-negative integer, or a whole number, that's green, and common divisor, d divides a and d divides b, and finally, a linear combination, d is ax plus by form, where x and y are integers. Let's prove such integer d exists. First, trivial case. Either a0 or b0, then we can force kind of like this. When a is greater than or equal to 0 and b is equal to 0, then we can devise a linear combination as a times 1 plus b times 0. That'll give me a. And a is greater than or equal to 0, so yeah, it's a whole number. And then, is this a common divisor? Well, a divides a, of course. And a divides b, well, b is 0, so everything divides b, so no problem there. You see? A times 1 is, a is 1 times d, because a and d are the same. And then b is 0, so 0 times d, yes, it's a common divisor. And as for the linear combination, it's already there. Now what if a is negative? Then we can devise this kind of linear combination, a times negative 1 plus b times 0, and because this is negative, we ended off with negative a, and that's a positive number. Remember, we started from a negative, so this time negative a, which is positive. So that's a whole number, and we can easily prove that this divides a and divides b, so common divisor as well. And as for linear combination, it's right here. And of course, we can do the same thing when a is 0 and b is non-zero. So that concludes the trivial case. So for the rest of the problem, let us assume neither a nor b is 0. Let's assume they are both non-zero. And then let us define a subset S of z plus like this. The set of all linear combinations of a and b which result in a positive integer. So ax plus by form all those that result in a positive integer. Remember the property of Z+? It is well ordered. So every non-empty subset has the smallest elements, the minimum, and that's what we want. So let's prove this is non-empty. Let's find an element there. How can I find an element there? Well, one way to do that is to put x is a and y is b. Then what do you have here? A times a, b times b, so we have a squared plus b squared, and that's greater than 0. Remember, both a and b are non-zero. So a squared plus b squared are both positive, so that's greater than 0. So what did you get? We found at least one element from here. In other words, this is non-empty, so there gotta be the smallest element, the minimum. And we're going to define d as the minimum. I said it backward. We're going to define d as the minimum of the set. And consequently, d is a positive integer because is a member of this set, which is part of C+, and that is in turn part of W. So that satisfies the first condition here, green. And then how about the second condition? Well, look at the condition of the set S. We have linear combination to begin with. So we have the third condition, the linear combination. So green came out easily. Red was there by design to begin with. We set up this mysterious set like this in order to accommodate this hardest part, the red part, the linear combination part. So looks like this one is easily done, but as a matter of fact, getting this set out of nowhere, that's the hard part, and that hard part was devised in order to accommodate this red condition. So as a matter of fact, as usual, the red part was the hardest part. But they're all done. We got this S, and then we proved that it's non-empty, and then consequently, we got the minimum. Therefore, we have green and red. All good? All right, now let's go to blue. Let's prove that D is a common divisor of A and B. Let's prove D divides A. Let's begin with a division algorithm. Divide A by D, and then you're going to get some QD plus R, and R is the remainder, so it's always greater than or equal to 0 and strictly less than D. Already, a proof by contradiction is forming here. You see, we define D as the minimum of this set, the smallest element, and here in step 3, we are beginning with a number that is less than D, a non-negative number which is less than D. So maybe this will draw some kind of contradiction, less than the minimum. Indeed, yes. Indeed, yes. What we are going to do is, in this expression right here, plug in D is AX plus BY right here. So AX plus BY like this. And then what you're going to do is to solve for R. We can solve for R. Flip that to the other side. What do you get? R is A was there before, and then QX, the 1 minus QX. Yeah, 1A was there, and QAX flip over, so we have negative sign. And then flip this to the other side, BQY. If you want AX plus BY form, A times integer plus B times integer form, then you can rewrite like this. In any case, it's a linear combination. Actually, we have this computation here already. Put AX plus BY in place of D and do your computation. As a matter of fact, I like this computation better. A times integer plus B times integer. Okay, let's copy and paste this thing over here instead. Okay, all right. Okay, now we claim this proves R is equal to 0. Is that clear to you? R is equal to 0? Well, R is greater than or equal to 0 and less than D. What if R is not 0? If R is not 0, that means R is greater than 0 and less than D, because R is bounded right here, greater than or equal to 0 and less than D. Among those, only equality here is taken off. Okay, and also R is A times some integer plus b times some integer form. So a times integer plus b times integer form, the linear combination form. So what conclusion can I draw? R is greater than 0 in particular, and it is a linear combination of A and B. Wait a minute, that means it's a member of the set S, right? So that means R, belong to S, yeah, greater than 0. So greater than 0, come on, greater than 0, which I just highlighted in purple, and it is a linear combination form, again purple. And that generated this, which I highlighted in purple. R belong to S. That's the definition. You see that? Linear combination, and it should be positive. So positive and that. Now what's left? This one I haven't used, which I'm highlighting in brown. So R is less than D, which I just highlighted in brown. That's the conclusion I got. R belongs to S, and R is less than D. But what is this D? I need a little bit more, so so what conclusion can I draw here? Maybe I'll just continue here. R is less than D, but D happens to be the minimum of S. So R belongs to S, yet R is less than the minimum of S. That's a contradiction. It can't be true. No element of any set is less than the minimum. So R is a member of S, and it's less than the minimum of S. Can't be true. It's a contradiction. So R has to be equal to 0. If not, blah, 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 okay. With this, can you understand everything? I'm not so sure. That's why I rewrote that part. And then we can go to the conclusion here. The remainder is 0, therefore D divides A. The desired conclusion follows. D divides A. What did we want to prove? We wanted to prove that D is a common divisor. We just proved D divides A. Now, can you prove the other one pretty much the same fashion? From the division algorithm like that, and the set of similarly, and use the same logic and conclude D divides B? Yes, you should be able to do that. If you want to do some exercise, then you can paraphrase that with different characters, of course. I'm going to leave that to you. And as a consequence, D is a common divisor as well. So we have all these three. Non-negative, common divisor of the linear combination form. We got the existence. We already proved the uniqueness and this additional property previously, so we'll say Bezout's theorem is now completed. And that concludes section 3. Good work. It was a major accomplishment.